Hello and welcome back to Calculus 1, section 3.9, derivatives of log and exponential functions. Thank you. So, we already discussed the basics of this lecture. Okay, fine, I'll leave it this. The derivative of e to the x was e to the x. And then we also said that the derivative of e to the ax, which you can use the chain rule for, is ae to the ax. So those are the ones that we already covered, and you are supposed to know these. So derivative of e to the 3x is 3e to the 3x. So those are the ones that we covered. Now, note that the base for exponential function doesn't have to be e all the time. It could be anything else. And also the exponent doesn't have to be x all the time, right? That's just y equals x. That's just a linear function, right? It can be also anything else. So from here, we would like to upgrade this formula into this general case that works for any example that you can possibly imagine. The first step, and the one that it's used most of the time, is the derivative of e to f of x. So the derivative of e to some function. Say you have e to the sine x, or e to the x squared plus 1, or e to the 5 tangent x. So you can have any function in the exponent. And to develop this formula, all you need to do is to use the chain rule. The derivative of e to something is e to that something times the derivative of the function. This is the formula which you will be using 95, 99, 90, whatever % of the time. This is the most frequent formula. Used. Now, this is not the most general case, because even though we generalized function up there for f of x, we still have base always is e. So the general case for something like this would be the derivative of b to the f of x. So any base, you can have 2 to the sine x, all right? You can have any of those. And the derivative for something like this would be b to the f of x times f prime of x times ln b. So this is the general case. This should be the boss equation, but unfortunately it's not. Most applications in the nature, most applications in engineering, sciences, are all off of e. Some are based on base 10, like pH calculations in chemistry and wave calculations in physics would have base 10, or your earthquake scale also base 10, and so on. So there is some base 10 through sciences, but vast majority are always e, which is why the formula above, the one boxed in purple, is what we would call the boss equation, because it's used almost always. The one on the bottom is the general case. Again, for purposes of mathematical gymnastics, we can always ask a question like, what's the derivative of 3 to the sine x? And then you will just follow the formula. The first tells you to copy what you see. The second one tells you to take the derivative of the exponent, which would be cosine x. And the last one is to put ln of 3. And you're done. There is nothing to simplify, nothing to combine. You can punch ln 3 in the calculator, get decimals if you care. So there is really not much to do here. Exponential equations, as I said, if you know the purple one, you are covering the vast majority of your life. And then it's also easy to upgrade into the one because it's just ln b that you're getting as extra term. Far more interesting is the story of logs. Logs.
Oh, okay.
Yes, a log. So, let's talk about everything regarding logs. Even go before. What's 2 plus 3? 5. Now, what's 5 minus 2? Good.
3.
And how about 5 minus 3? Good. That was some quick computation. How about 2 times 3?
6.
And 6 divided by 2?
3.
And 6 divided by 3?
2.
So do we see that addition has subtraction as the opposite, and you can retrieve each one of the terms that you added?
Yeah.
For multiplication, we have 2 and 3 as factors, and we can retrieve each one of those factors by division. Now, what's 2 cubed? 8. And what's the cube root of 8?
2.
Great. Now, how do I get 3?
Find the log of.
Yep.
You find the log of 8. The base is 2.
Log base 2 of 8 is 3. That's where they fit. If you never understood where the logs fit in the universe. So, it's mathematical operation. Just like addition or subtraction, it has its rules of what, right? You have 2 input numbers, like any other calculation that you see on the entire, right, chart over here. Every single operation you see is operation between 2 numbers to obtain a third number. Right? 2 times 3 is 6. You use 2 and 3 to create 6. 5 minus 3 is 2. Well, if you combine 2 and 8 using a log, you get 3 on the other side. So try for once in your life to be nice and not discriminate, because this is the only operation that has letters in it and not a cute symbol, right? Be nice. Accept logs in your heart. Is log a function? No. Addition is not function. Multiplication is not function. It's operation. Now, do we actually create functions with logs? Sure. But you create functions with everything else. X plus 3 becomes a function.
Yep.
X minus 2 becomes a function. 2x is a function. 6 over x is a function, right? So, logs are not functions because they exist. It's operation. You create a function by saying log base 2 of x equals y. It becomes a function then, because you involve independent variable x to come up with some output y, right? Your calculators compute logs, they compute only base e and base 10 logs. So if you have log base 10 of x, then we just write log x. So when you see log without base written, it's understood it's 10, and in your calculator the capital LOG button is the one that is base 10. If you need to calculate log base e of x, we have a lazy notation for that as well. It would be ln of x, which is capital Ln button on your calculator, and that's base e. These two bases are most common bases that we use in sciences, and you pretty much don't see any other bases ever. So there are no buttons devoted to those. There is a change of base formula that you can use to convert your non-wanted bases into either e's or tens. Some calculators don't even have both of these. They have only one of them. So Mathematica deals with only base log e, so ln, even though they do write log, which is confusing, but such is life. So change of base formula, we'll take log of base b of a and change this into log a divided by log b if you want to use base 10, or ln a over ln b if you want to use base e, which is ln. So that's change of base, and you only use this if you need to compute stuff using calculator, right?
Does it say calculator?
Yeah. The most important formula that you get to learn is the connection between exponential function and logarithmic function. You can already see that connection here.
Yeah.
So conversion is a raised to the b equals c, converts back and forth the log base a of c equals b. So this is something that you have to use all the time to solve either exponential or logarithmic equations. So conversion is extremely important. So far we understand that logs are just an operation between two numbers to obtain a third number. We understand that the most frequent bases are base 10 and a base e. We understand that the log is inverse of exponential function because it can, through this conversion, it can convert back and forth. And there are two what I call cute formulas. One of them says that log any base of 1 is equal to 0, and log a of a is equal to 1. So these are some cute formulas that
would be a to the first power.
Yes.
So that would be a.
Yeah, a to the first power equals a.
0 power.
A to the 0 power equals 1, yes. And now, if you don't remember these formulas, it's time to recall these formulas because we are going to use them. And those are the three formulas that convert log base a, or you can do ln, doesn't matter, of xy into a log ax plus log ay. Difference, log ax over y is log ax minus log ay.
It's like the same thing with the limits.
No, these are actually different.
All right.
Because these are the products going into sum and quotient into subtraction.
Yeah.
And then we have log base a x to p is p log base a of x. These formulas are used to either compress or expand logarithmic equations and expressions. And in pre-calculus, you were mainly concerned with compression. Well, welcome to calculus. We are going to be primarily interested in expansion. Just like, right, when we talked about last time about function composition, right? And you were mainly interested in making new functions out of old functions, composing, but then calculus is primarily interested in decomposing. So the same thing here. Most of the problems you did in pre-calculus, vast majority of problems you did in pre-calculus was to compress logs into a single log. In calculus, as you will see soon, we are interested mostly in expanding functions to as much as we can. Believe it or not, this is entire log lecture, all of the formulas and everything pertaining to logs dumped into one spot. The only thing we didn't talk about are the properties of log graph with the vertical asymptote at 0 and what the shape looks like. But all of the formulas pertaining to logs and the concept of what the log actually is right there on the pile. So now we are interested in derivatives of logarithmic functions. And you already know the derivative, because we mentioned it earlier, the derivative of ln x. Who can remember the derivative of ln x? 1 over x. Excellent. So this is the one that you already know from before. Well, the general case, not the general case, the more interesting case would be the one that replaces x, the argument x, with any function f of x. And that's the one you will be using most of the time. So, the most important formula is ln of f of x. So this is ln of f of x, right? ln is applied to f of x. And it's simply f prime of x divided by fx as is. So you copy the function as is in denominator and you take the derivative in the numerator and you're done. So this is the formula that you will be using most of the time. This formula is the boss.
Or the derivative of e of x?
Yes. So now that we are going to write the general case, the derivative of log of any base b of f of x. So again, you don't see log base 3, log base 7, log base 12, right? You see log base e, which we abbreviate as ln, and you see log base 10, which is just log without any base. So those are the two that are everywhere. So this formula, again, yes, it's the general case, but it's very rare to see it used. What is this one? Well, it's the same as what you had before, the f prime of x divided by f of x, except you will have ln b in denominator added. So this is the general case. Where you can pick any base, any number for the base, and any function in the argument of the log. So you can calculate log base 7 of cosine x. You can use this formula to figure out what that. Well, let's do it because we can. So what's the derivative of log base 7 of cosine x? Copy the function cosine x as is in denominator times ln 7, and derivative of cosine is negative sine x, and negative sine over cosine, that's negative tangent, so we have negative tangent x divided by ln 7.
This is defined further?
No.
Okay.
I mean, you can find the decimals for 1 over ln 7, but no one cares.
L would be the derivative of log
So basically, taking derivatives of ease is the least amount of effort in life, followed by derivatives of logarithmic functions. As simple as, usually the best way for you to learn is to do this. Everyone is looking at the purple formula?
Yeah.
Ready?
What?
The way to remember. Control C, Control V. And then you take the derivative. Yeah. Yeah, copy and paste. Very good. So Control C, Control V. One more time. Control C, Control V, and then you take the derivative and you're done. Very simple, right? So what can you expect? The derivative of ln of x sine x, let's say. I have to put one of these problems, otherwise our clan over here is going to complain that the problem is spicy. Alright, try that. I'm going to go look for hydration. Oh.
Mostly product rule here, right? For x on x. Right.
What is this? It's the product rule within Ln, so it's a double chain. Great. Let's go. As soon as you see derivative of Ln, division line, Control C, Control V. That's always the start. Then you look at the function you have here and do the derivative of that function for the numerator. Well, it's a product rule, so we have copy the first derivative of the second plus copy the second derivative of the first. We don't need to write this times 1, so we'll just leave it there. Nothing cancels, so that's it. We are done.
Okay.
You don't need an ln. Yeah.
The title for the last part of this lecture, the subtitle or whatever, is Logarithmic differentiation. Just to mention one more time, the word differentiation means process of taking the derivative, obtaining the derivative.
Yep.
Good. All right. So you guys said we should have some spicier problems. So the derivative of x cubed sine to the 6x divided by 4th root of x cubed minus x squared plus 1. That sounds like a good problem to solve. Now, what do you have in this problem as you look at it? What do you have? Chain rules, right? Chain rules.
Yeah.
Because sine to the 6 is a chain rule, and the 4th root is a chain rule, and there is a product rule, and the overall is the quotient rule. So to solve a problem like this, what you do is you first, well, after you're done cursing, obviously, you turn the notebook sideways, you put the division line in 2 lines, and then you slowly start, and by Thursday next year, you'll be done.
Is there an easier way to do this?
Yes, glad you asked. The easy way to do this problem is to look at it and then immediately write down the solution in a factored form. That's the easiest way to do the problem. See, the way to do this is to just write x cubed sine to the 6x divided by 4th root of x cubed minus x squared plus 1 times, and then here is the other part of the solution. The first one would be 3 over x plus 6 cotangent x minus 1/4 of x cubed minus x squared plus 1, and then 3x squared minus 2x, and that's it. So that's the answer. So that will be the derivative.
Wow. Oh.
That's the easiest way to do the problem. Obviously, right, if you go into all of these product rules and quotient rule and chain rule, right, you're bound to make a mistake somewhere because you weigh just a lot of that stuff. This logarithmic differentiation takes on that ancient martial arts kind of approach. You know, when they in martial arts, when they say the more opponents you have, the easier it is. Well, that's pretty much this. The worse it is, the easier to do the derivative. So if we pile up additional product rule and chain rule and so on, it just gets...
I don't see where you got this values from.
Well, shall we learn that?
Yeah.
Now imagine if I would, like Morpheus, now I go, you know, what if I told you, right, that every derivative you took so far in this chapter can be done this way without writing any intermediate steps, without knowing any formulas, without just, I know, right? Which is why I usually have, you know, one or two students in a class that actually invest few hours in sorting this out mentally so that they can do any derivative, doesn't matter how complicated it is, like that, and then just keep freaking people out. Especially you go to Calc2 and they're writing something and it's like, you know immediately the derivative answer in the factored form without even writing anything down. Wouldn't that be cool? Of course it would be cool, right? Now, in the background, there is a lot of math that is happening, and that math depends on these red formulas, and it depends on the purple box. So two purple boxes you see over here are all you need to transform any derivative you see into a biggest joke ever. And as I said, the more complicated it is, you don't care, because the first three rules are turning all of the chain rules and all of the product rules and quotient rules in basic additions and subtractions, which is haha. And then each one of those individually would be a single ln derivative, which is solved by the bottom equation when you take in the derivative. So these four formulas together take any derivative you ever learned and completely make a joke out of it. Now let's take a look at the simplest possible example and then upgrade to something that can make you cool when you go out with your friends, right? And someone, you know, in that you have a conversation or something, and they say, what do you know? I know this. What do you know? This is why no one argues with me. It's like, what do you know? Yeah. I have kids. Oh, really? There's a PhD in that? Nice. I had no clue. Anyway, so let's take a look at the basic example. For instance, say you want to take the derivative. Right, you're out. Let me paint the picture. You're out with your friends, right? You're having casual conversations, gossip, whatever you do, right? And then all of a sudden, x cubed sine x comes up, right? The derivative. Like that's, yes. Could be also Thanksgiving dinner, right? You ever had anyone from Thanksgiving dinner, like a relative or someone, say, hey, hi, what's new? Perfect opportunity to put this on a table, right? Like, I can differentiate this mentally. And if they're still looking at you, try to ask them to spell differentiation. See if they're going to drop some F's and stuff. I mean, the letters as they spell. All right. So what is the secret, right? The first order of business is to define y as x cubed sine x. Clearly, we can do this with product rule, right? Yep. It's no-brainer. But we can also use the sledgehammer. So you define whatever you want to differentiate as y. And then you apply ln to both sides, which is going to be this red ln to both sides. Now observe that the argument of ln on the right-hand side, which is the black writing, is a product of two things. And by our ln formula, when you have a product of two things, it breaks into addition of two ln's. And that's what kills the product rule, which is why this is so cool. So as soon as I have ln of whatever is here, in the next step, the product rule is dead. No more product rule. And that's a simple algebra rule of logs. Now you still have this x cubed. And let's say you don't like that either. Well, you take that 3 and you kick it outside of log because you can. That's another rule. So the entire problem now is a complete joke. You expanded your function into these very basic functions. ln x, ln sine x. You can differentiate that with no issues. ln y, so now when you expanded everything, right, you are at the point where you can hit this with the implicit derivative. What is the derivative of ln y? 1 over y, keep talking.
Y,
dy dx, exactly. On the right-hand side, we copy 3. What's the derivative of ln x? 1 over x, bueno. And what's the derivative of ln sine x? No, you will put sine x on the bottom. That's a Control-C, Control-V. And then we put the derivative on top, cosine x. Great. Oh, that turns into a cotangent, huh? Nice. So now, you see this 1 over y? Move that to the right, because dy dx should be so on its own, yes, solo. So dy dx is equal to y times 3 over x plus cotangent x. What's y? Y was the original problem, right? Remember how my long solution had that feature of copy the original problem and then do some voodoo magic over here? Right? So dy dx is y, which was x cubed sine x, times 3 over x plus cotangent x. Hey, look at that. Well, that's factored, fully factored. Have we done a single product rule? Or a quotient? Or a chain? No. We did algebra, and then we differentiated ln f of x. Any problem you have done so far can be, with this technique, completely broken down into these basic ln functions and then differentiated easily.
How do we get the? Okay. Oh. Are we doing ln f of x? Works.
Yes, that was ln f of x. Let's do a quotient rule problem you didn't like at some point in life, let's say. Say you have the derivative of x plus 3 divided by the cube root of what? Pick something. X squared minus 4. You can say thank you. Save your skin. Well, this particular problem here has a quotient rule, and then there is a chain in denominator, right? Right. Well, let's put this through the ln machine, see what comes out on the other end. Y equals, leave some space, x plus 3 because you need to stick in ln, right? So leave some space. X plus 3 divided by the cube root of x squared minus 4. So you are defining what you're looking for as y. And now you insert ln on both sides. On the left hand side you have ln y. On the right hand side you have ln of x plus 3 minus, because now you have division. Kick 1/3 in front of ln because that's the exponent. And wow, all of the chain rules and all of the quotient rules, everything is dead and done and gone. And all we have are just basic ln's to deal with. Cool, huh? Time to take the derivative in respect to x. What's the derivative of ln y? dy dx. That's extremely important. On the right hand side, what's the derivative of ln x plus 3? Well, x plus 3 goes in the denominator. Remember, Control C, Control V, right? X plus 3 goes in the denominator. And what's the derivative of x plus 3? 1. Perfect. Minus 1/3. Control C, Control V, which is x squared minus 4 in denominator. What's its derivative? 2x on the top. Great. Time to move y to the right hand side. We have 1 over x plus 3 minus, you can call this 2/3 x over x squared minus 4, and then replace y with what y is, which is the original function of x plus 3 divided by the cube root of x squared minus 4 times this term, well, this parenthesis, and we're done. Here's a problem for you guys to enjoy. What is the derivative of sine x raised to the tangent x? Because we can. It's okay to talk to the people sitting next to you if you like them. No, thank you.
Yeah, that's what I'm saying.
Because the derivative over the usual, like over the original, and then you can make tangents on other cosine, so everything cancels. Yeah. And then you just get the same thing. Because ln of sine of x is cosine of sine. And then tan is sine over cosine, so everything just becomes one.
You can do every derivative this way.
This is so
Why
much
do it
easier.
any other way? Yeah. Why do it any other way?
Oh, we had to build up to this, I mean, right?
Is it just the same thing?
The elevator is out of service until August 1st, which is this course will be all long over.
So one I've reached is, so boom, what have you reached? Yeah. One. You got that as the derivative of tangent?
No, you didn't.
Y L then to, I'll put it in here.
Sin x. Sin x to tangent x power. Just multiplying both sin x and tangent x into ln sin x and ln tangent x.
Logarithms, which is the ln sin x and tangent x back. We use the one logarithm to the tangent x.
Is that how it works?
Yeah.
Okay, I wasn't aware. Search.
Yeah.
Is tangent x? This is a lot.
sin x.
So do we all have the same?
Sin x.
And now I have a product rule here. So see, product rule is still relevant for some of these more complicated cases. 1 over y, dy dx, copy tangent x, and then you have a sine x, and then cosine x goes up there, plus ln sine x times derivative of the tangent is, very good. Now, everything here drops because tangent is sine over cosine, and then times cosine over sine, so they just cancel. You get 1. So dy dx is equal to, yes, Chewbacca? I thought I heard you. Sine x tangent x, 1 plus secant squared x ln sine x. A little bit complicated, but not that bad. Exam question from 2 years ago? 3 years ago? Past exam question. How about that? And you will practice that at home. Same rules. ln 2x drops down, you have the product rule, and then you just, everything unfolds. So it's cool.
X over 2x, right? Yeah.
All right. We are going to finish a short lecture tomorrow, maybe 20 minutes or so, 3.10 or whatever it is, and then work on the lab afterwards. This question, the last question, is something for you to practice at home and enjoy, in addition to the homework that it's open on the MyMath Lab. Bye.